Here we discuss our stress bounding condition if we now no longer assume that there are no forces inside of the interface. So we're no longer assuming this, and before we can write our equation, our boundary condition, we need to discuss what kind of forces are transmitted inside of an interface. So before we continue, we need to discuss a little bit about the nature of those forces inside interfaces, which are called surface tension forces. But you can also hear them referred to as interfacial tension, interfacial forces, interfacial tension, or capillary forces. Okay, so let's consider our interface again. Here again we have a fluid region 1 above our interface, fluid region 2 below the interface, and here we are isolating this little piece S of our interface, and we are asking the question, what are the forces applied inside of this surface? So here note that so we have this piece S of our interface, which is, this is arbitrary and this is imaginary, but it is separated from the rest of the interface by this contour C. So here again we are asking the question, how does the material outside, how does the interface, which is outside of S, of our contour, what forces does it impose on the interface or the piece of the interface, which is S here? And the force which is applied is what we call the surface tension force. And surface tension I will in this class often represent by the symbol gamma. And then units of surface tension are newtons per meters. And you have surface tension in any really interface between two fluid. So for instance, you have surface tension at an fluid gas interface. But you also have something very similar, actually the exact same thing, but which sometimes will be called the interfacial tension, which I'll also always call gamma. And you refer to that as an interfacial tension at a liquid-liquid interface between two immiscible fluids, liquids. All right, so one thing which you may or may not have noticed, but here gamma has units of newtons per meters, right? So it has the units of an energy per unit surface, right? So these are also joules per meter minus 2. So it has the units of a surface energy. And indeed, one way to think about interfacial tension is to think about it as from an energy perspective. So in thermodynamic equilibrium, you know that the free energy is minimized, and one way to think about surface tension is as it relates to the free energy of the interface or the surface energy by simply writing ES, which will be the surface free energy, and the surface free energy is proportional to the surface, right? The larger a surface, the larger the surface free energy, and so the energy is minimized when the surface, when your body takes on the shape of the minimal surface, right? So that's what comes out from thermodynamics. And so the surface tension then is simply this coefficient of proportionality. So there's the constant that relates your surface free energy to simply your surface area. Here note that the surface is, again, this is an energy, so it's in joules or in newtons times meters. Your surface is in meters squared, such that your surface tension is in Newton per meter. So you can think about the surface tension as a force within the interface which makes sure that the interface has a minimal surface area. And it turns out that if you take the equivalent definition, but from a force perspective, this is equivalent to representing, as we were discussing, the force exerted by the interface outside of C onto the interface which is inside of C as simply a force a line force, so force all along of this contour. So the surface at the outside exerts onto S a force which is inside of the surface, so it's in the direction tangent to the surface, but in a direction which is normal to the contour and of a constant magnitude, which is gamma. So here think about this force as a force which is going to try to flatten out every single bump and flatten it to make it as flat as possible, or maybe not to make it as flat as possible, but to reduce the surface area as much as possible. So if we write this in words, this is equivalent to a line force F equal to a constant gamma, this is our surface tension, times lambda, where lambda is normal to our contour and it is tangent to the interface, so it is inside the interface. So this is how you can describe the forces exerted inside of an interface. Now going back to our little momentum balance onto our controlled surface, our control volume here. If we now include effects of surface tension, then we have to take into account those forces. So now that we have defined this control volume that defines as a piece of the interface S, and therefore in addition to all of this, we have those forces here. This is lambda, this is gamma times lambda, and we have a whole distribution of these forces. So this translates into an additional term here, which corresponds to an integral on the closed contour C of gamma times lambda dl. So gamma lambda here is our force per unit length, and dl is a piece here, a differential element along our contour. That would be a small dl. Okay, so we can do the same analysis as before, right? We split the surfaces. This term goes away, this term goes away, this term goes away because it becomes small when epsilon goes to 0. And then we are left with the top and the bottom and this additional contour integral. And that yields our boundary condition, which has, so our boundary condition at the integral level has now this extra term here. Now this stress boundary condition, we could do the same as what we did for the momentum equation and just change this contour integral into a surface integral, but here the differential geometry is a bit more complicated, but essentially we do the same thing as what we did with the momentum equation to deduce the boundary condition at the differential level. And at the differential level, this equation here, right? So this equation here, you just apply some mathematical stuff from differential geometry, and it yields two stress boundary conditions, one in the normal direction and the other in the tangential direction. So we'll start with the stress boundary condition in the normal direction first. And so this boundary condition is not here. This is the difference between our stress vector in region 1 and region 2. And so this difference between those two stress vectors we are going to project onto the normal direction, right? This is equal to the surface tension times the mean curvature, which is equal to 1 over the radius of curvature in one direction plus 1 divided by R2, which is the radius of curvature in the other direction, and I will explain that in just a second. But first note that this here is really, this is nothing mysterious. We've discussed that before. This is our stress inside of fluid 1. So this is minus P1 times the identity plus 2 mu times the rate of strain tensor in region 1. And this here is, it is taken at the interface, but in region 1. And likewise, this is the stress tensor in region 2. And again, this is taken at interface 2. This here is a constant. This is the surface tension. And this here is the average curvature with R1 and R2 being two radii of curvature in orthogonal directions. So how can we understand those two radii of curvature without going into too much detail, mathematical detail? If you have a surface, this is my surface here, and say the surface is slightly deformed, right? At every given point, this is the point at which I would write, for instance, my stress boundary condition, where you can define two orthogonal directions, this one and that one, right? And so if you consider the intersection of your interface inside of one of these directions, you could have, if you're fitting with the closest resembling circle here, that could be one radius of curvature, that would be R1. But if you looked at the same curve and you looked at the shape of the interface in this plane here now, then you might have another radius of curvature which is much smaller, right, or larger, or it could even have a different sign, right? So this here, in this plane here, the intersect here might be R1, R2, sorry. All right, so this is the stress boundary condition in the normal direction, and then you also have a stress boundary condition in the tangential direction. And so this one we can write as the following. Again, we have the stress vector, a difference between, so the stress vector in region 1 minus the stress vector in region 2. And this difference between the two stress vectors we project onto the tangential direction. Note again that this is only non-zero if the surface tension, if there is a surface tension gradient. And note that this is called a Marangoni stress.